Thank you for joining today's webinar on increasing awareness of safety risks to healthcare team members from infectious aerosols in perioperative spaces. I'm Vic Tatine, the president of Indiana Society for Healthcare Engineering, also known as ISHE. This program is presented on behalf of Midwest Healthcare Engineering Conference. Watch for more information coming early next year. It's my pleasure to introduce our speakers today. Dr. Jennifer Wagner. Jennifer is a co-founder of OnSite LLC to focus her expertise on reducing the rate of healthcare-acquired infectious HAIs through consulting, education, and research. She has worked with prominent healthcare organizations to improve infection prevention. She has also worked with innovative product designers to test the efficiency. Damon Greeley. Damon, also co-founder of OnSite LLC, to further his passion to continuously improve infection prevention in the healthcare built and operations environment through actively engaging innovation and creativity. As a member of OnSite's research team, he actively investigates newer methodologies or technologies that improve infection control coupled with the best life cycle costs. And Brent Lloyd, surgical nurse and contamination control professional. Brent works with OnSite LLC to bring 22 years of clinical consulting and contamination control experience with a focus in the healthcare sector. He worked as a registered nurse in the OR, specializing in orthopedic, and as clinical consultant for healthcare companies with respect to contamination control products or solutions that employ in their facilities. Before we begin the presentation, I would like to thank today's sponsors, Midwest Associates and BSA Life Structures. Both have prepared a short video introducing their companies.
Good afternoon to our ISHE friends. I'm Stacy Carey with Midwest Associates. We're happy to sponsor this virtual meeting for November and glad to see everybody back together. Midwest Associates provides commissioning, test and balance, construction quality assurance, and safety services for the healthcare and other industries. In addition, we provided isolation rooms during the COVID pandemic, and we provided construction quality assurance services for new projects. Our mission at Midwest Associates is to work with the owner and the project delivery team to deliver a project that works according to design and delivers premium results for our owners. We've been around since 2007 and over the years have worked with many healthcare clients. We've had the privilege of working with the VA, Eskenazi, Franciscan Health, IU Health, Community, St. Vincent, and many other clients in the market. Thank you again for the opportunity to continue to serve you.
This time, I would like to turn over the presentation to Damon Greeley. Damon, take it away.
Thank you, Vic. And good morning, everyone. We would also like to thank our sponsors, Midwest Associates and BSA Life Structures. We've worked with them for many years and collaborating on the projects we've done together. We also would like to thank ISHE and the Midwest Healthcare Engineering Conference, as well as the ISHE Central Indiana chapter. So beginning our presentation, we changed the title a little bit to really reflect what we did when we were approached by Dr. Frank Dexter and the American Society of Anesthesiologists. So they came to us and they said, you know, we are concerned about our staff, our associates who are anesthesiologists and their risks of working in procedure rooms in which there were SARS-CoV-2 confirmed patients or even patients under identification. So we're going to walk you through the process that we applied and as well as the research that we conducted to help inform of these risks as part of a risk assessment. And it will include epidemiology, toxicology, pathogenesis, and aerobiology components. Today's learning objective will be that modern ORs are designed with concentrated air delivery over the sterile field. However, when you're protecting the sterile field and protecting particles from coming into or pushing them away from, what risks are created potentially in the periphery of the room? And as simply put by Dr. Dexter, you know, does standing along the wall really a safe position to be on behalf of our staff and other surgical team members with respect to potential exposure? And then finally, what can a facility do to better understand these risks and to mitigate them and keep staff safe? The other thing I would like to note is that when we're talking about aerosol generating procedures, we'll refer to that term. Once the patient is in the room and administered propofol or a paralytic agent, right, they are no longer coughing or sneezing, right? They're not discharging aerosols from the lungs, right? They are under anesthesia, general anesthesia through intubation. So what we're talking about is the risks for SARS-CoV-2 virus that is in bodily fluids. They're being emitted from the procedure itself, whether that's blood or pus or sputum or something else that is coming from the body. So we like to call it kind of the bugs, the drugs, the plugs, and the lugs. And as you can see here, this is a typical operating room, and we have our clean air zone, which is ISHE 170 prescriptive method for distributing air, supply air above the surgical table. What you also see, in addition to the room configuration itself, is darker circles, which we refer to as reservoirs. And in these reservoirs are microorganisms that are either deposited there or transferred there during the procedure. And as part of the activities that are happening, and you see a circulating nurse just doing his or her duty within a 20-minute time period, and how many times that those reservoirs are crossed with potential risk for cross-contamination. So those are the bugs. This is an SEM view of a surgical instrument that is contaminated. So we know that these instruments are contaminated and become contaminated during procedure. To combat this, we use prophylactic antibiotics, right? Vancomycin is just one example. It comes in liquid form, it comes in powdered form, and it has various uses depending on the surgical team and their approach. What we also have seen emerge or maybe become more prevalent, what we call the plugs, is the concept of electrification for air purification or potentially manipulation of molecules through chemistry. And we recently have had several manufacturers of these products and systems admit to us in full disclosure that they have lost control of the use and the application of their products during this pandemic. And that's just a cause for concern that these are being so rapidly purchased and utilized that they need to be understood as part of the process. And as we'll go through the presentation, some of the things to be concerned or a lens to apply to these is knowing that there are people in the room, right? Human beings are the source of these contaminations in many cases. And we can't electrify the room to a certain degree, depending on your technology, without potential harm to human beings. And the time factor by which some of these aerosols travel is a very short period of time. So do you have enough time for an effective kill? Because if you don't kill the organism, if you only modify its DNA, you've now created a superbug. And then, of course, to make things worse, we know that there's just inherent or inert objects such as lint, right, or the shedding of PPE that is continuously being generated. It's found in wounds. If you're a mechanical engineer or in maintenance in a hospital, you have to clean these out of your ducts and grills and airflow sensors, which are the lugs, right, the luggage of the carriers. And of course, all these things microbially are invisible, and we have to help make them more visible. So just as an acknowledgement from our team, we've studied the virus for the past 6 months. We know some, but we don't know everything. And we're continuing to research and discover. We don't have any conflicts of interest except for Beacon and AirStat. And Beacon is our proprietary and patent pending algorithm that is used to predict risk of in-room contamination during procedures. And that is assisted by air visualization, or the AirStat product. And it's really the reason why the American Society of Anesthesiology and anesthesiologists approached us, right? They needed answers. Some of our work is helpful and to inform them. And of course, they want to manage the risks or prevent them or even mitigate them. So we've used these tools to inform and produce our paper. Here are some of our other collaborating institutions, including ISHE National, the NIH, Center for Health Design, American Journal of Infection Control, and others. We have a multidisciplinary team because these are multifactorial challenges that we face. We have 4 MDs, we have 6 PhDs, we have microbiologists, infection preventionists, industrial hygienists, we have engineers, we have nurses, we have other clinicians, all that are coming together to bear on addressing these issues that we face. Here is the paper that we're going to go through today, as it was published in American Journal of Infection Control about a month ago. We also have 8 other peer-reviewed journal publications that have all been published in the last few years, and we can have that provided for you if you just reach out to us with our contact info at the end. We also want to acknowledge our other contributors to the paper, which is Dr. Troy Markle, who practices here in Indianapolis, and Dr. Gormley, who was with Vanderbilt when we started doing research together, and he has since transferred to Middle Tennessee State. When we are looking at all the factors, right, COVID-19 is certainly just one. It is significant, but it is not the only one. There are many others. We have to look at the microbiology and the toxicology of the space, right? We are dumping a tremendous amount of chemicals into our facilities right now to try to minimize or address the risk of virus. We have to look at physiology of the patient and the occupants. Are you healthy? Are you not healthy? Are you incapacitated? We have to consider ventilation and cleaning methods. And probably most importantly is people and process, right? Things have to keep moving forward. We have to keep treating patients and doing good. And those processes contribute to the health of our communities. They contribute to the viability of our institutions. And we can't disrupt those. We have to optimize and work with those together. We study many different forms of transmission: airborne, contact, fomite, aerosol, droplet, nuclei, and particle. Those terms used to be esoteric to many of those that are just in research and infection prevention, but of course with the pandemic they're becoming more household terms. And we've conducted now 100 experiments. I wish it was 101 because 100 almost looks unbelievable. But we've conducted 100 experiments by which we are studying all these factors to determine what is correlative, what is predictive, what is preventative, what is point prevalence or incidence, and how they are related to each other. We do address, because of our team, the risks holistically. And the only thing that I want to point out is that we are no longer entering, but we are here in a post-antibiotic and superbug era. And if you haven't realized that, just pick up the news on some of the recent publications. As a matter of fact, there's now microbes that are resistant to bleach. And because of that, we are now in the end game. And many of you know that I'm a Marvel fan, so I always have to work something in with respect to it. But in all seriousness, we do need to go back in time to work with organizations such as Clean Room and pharmaceutical manufacturing, pharmacy compounding, OSHA, even overseas standards, to know and learn what they know about keeping rooms clean to protect patients, so we don't have to continue to dump copious amounts of prophylactic antibiotics and chemicals to deal with the issue. We're also working with the University of Oregon with SARS-CoV-2 or other airborne viruses with regard to the risk of transmission, and modeling different parameters, right, based on the volume of the room or the ventilation, potentially a secondary recirc or cleaning device, the time in the room, the time of exposure. And models can be very helpful, but they must be reconciled with the three-dimensional reality, which includes the proximities, the equipment, and the movement within the space. So the perfect illustration would be here is to show that occupant A appears to be infecting occupant B if the discharge is infectious, and occupant C appears to be in a safe distance or location. However, if I throw in airstream at carrier velocities, which is very common, right? There are cross drafts within an operating room or other rooms or other spaces. And we look at it in a three-dimensional reality. Now we see there's a different story, that occupant B appears to be in a little bit safer position than occupant C. And that is why we've used and worked with VIU Inside in collaboration with 3D visualization of airflow patterns. We also want to thank AWARN in our collaboration with them, and really thank all the heroes, not only nurses, but technicians, medical doctors, those who are in supporting roles, those who have put their lives on the line in risk for this pandemic to serve others. And I would just like to take 5 seconds to pause and remember those heroes that have fallen. So this is something that's vital to understand, and this comes from Dr. Lindsay Marr with Virginia Tech. She is a collaborator with CDC and other virologists and institutions that are studying this virus. But the one thing she said is it is the size of the carrier or the droplet aerosol that defines the transport of this virus in the environment. The size of the virus itself is irrelevant. And that's a pretty strong statement. And if you can see on the right side, the image, you know, the virus is very small, 0.1 micron or 1 nanometer, versus the respiratory fluid, which really begins at about 0.5 micrometers and goes up. And we also know that the survivability of this virus is dependent upon it remaining in its innate biological fluid or a synthesized fluid to keep it viable. If the virus breaks apart, if the droplet evaporates, it only becomes droplet nuclei and virions. And as we know, there are hundreds and probably thousands of studies out there, but if you want to filter that down to understand more detail about infectious aerosol transmission, this is a differentiator. It's one thing to detect virus or virions by using RT-PCR, right? That method only says that you've detected RNA material. It does not say that you have understood that the virus is infectious or has an infectious dose. What you need to do to understand that is whatever you're recovering from the air needs to be cultured. And one culturable method is called a plaque assay. So the virus is captured in its innate biological fluid or a synthesized biological fluid to keep it viable. And then in that inoculum is overlaid on a petri dish that contains bacteria. And then the virus begins to attack the bacteria, right? If it's viable, it's doing its thing. It's staying viable. If it is not culturing, if it is not doing its thing, then it was either dead when you collected it, or actually viruses aren't alive, they're just denatured. So it was either denatured when you collected it, or in the process of collecting it, you denatured it. Either way, it is going to only give you an inconclusive result. So another thing to consider when looking at virus and infectious aerosols, and we have this list of references, but it comes from the University of Toronto, is that particle sizes that are greater than 10 micron, 10 to 20 or larger, are going to settle out rapidly, right? They're going to be in a droplet form. So they're not going to travel very far. And of course, if you're masked, they're going to stay in your mask. But the other point from a physiology standpoint is they're not going to settle in the lower respiratory tract, right? Which is where they become infectious. And just a point of note that your nose cavity, right? Your nasal cavity can collect these virions, and you could be tested for that, but it doesn't mean that you are infectious or actually have COVID-19. So by that definition, being less than 0.5 is not going to be an infectious dose, and greater than 10 micron is going to fall out by gravity or not be capable of being deposited in the lower respiratory tract. Our risk assessment particle size focused on 0.5 to 10 micron. So a little bit of background on our research and how we look at this from an infectious risk prevention standpoint. We've spent many hours in operating rooms. We've put in a number of sensors to collect microbial data, particle data, information about the environment, information about traffic, workflows, processes, and categorize these from our 100 experiments plus. And we've done this in both in vitro, which is a simulated procedure, and in vivo, which is a live procedure. And as we understand these conditions and the amount of contamination levels we measure, we're able to produce a risk map or a risk picture because these data points become predictive. We can start to understand what the risks of contamination are by the data points we're able to study and capture in real time. So what this algorithm looks like is we have an environmental quality index on the y-axis, right? That is the number of environmental or utilization parameters that are out of range versus the level of contamination that would result based on that range and the activities that are happening in that particular sector. So as the environmental quality index goes up, the algorithm predicts that the colony forming units for bacteria or fungi or plaque, in the case of viruses, will reach a certain level, and at a certain level it is deemed to be not acceptable, and a mitigation or reduction of risk process must occur. When you look at that across the typical operating room, you see it in the form of a risk map. And then, of course, we simulate the operations that take place, such as moving Mayo stands, moving back tables into place, moving X-ray machines, so we can understand the entire risk picture. And then the sampling can be taken so that we understand what the levels of contamination are during these procedures to confirm and reconcile with our algorithm. We also know, because of the amount of particle data that we're capturing, what types of procedures generate the dirtiest space or the largest amount of particles in the space that are potential carriers for these organisms or aerosols. Again, we're not talking about a patient breathing, right? We're talking about what is being performed in the room, aerosolizing blood and other bodily fluids. I'd like to now turn it over to Brent Lloyd to talk to you about in-room staff safety during a procedure.
Thank you very much, Damon. Appreciate it. When I was introduced as a circulating nurse in the OR, and I worked in there and specialized in the orthopedics at my hospital where I worked. And during this, there are many things during surgeries that we are trying to coordinate. Different procedures, different doctors, they all have their special cards for each procedure that they're setting up. We're kind of like, as a nurse in that as a circulating nurse, we're kind of like an air traffic controller with what's going on. And what we're looking at and understanding, or what we've learned in our research, is that these bioaerosols can move very quickly in these ORs. And we are typically not aware of these bioaerosols because they're invisible, and being aware of where the diffuser grills are, where the supplies are, where the exhaust grills are, and what's going on is we haven't been able to look at that in the past. This research has brought that to the forefront. And what we've determined is that these particles move fast, and it can be as much as can travel across the room in 40+ seconds. So as we mentioned in the previous slide, being an air traffic controller, there are opportunities to transmit and trap these pathogens in these environments. Looking at the variety of these pictures here in the top left there, we're talking about the sterile field, contaminating the sterile field. What's going on there? How is that set up? Making sure that everything's on the table that we need. That's things going through our mind as a nurse. The bottom left is the C-arm. Did the C-arm get wiped down from the procedure where they were just at before? Is the X-ray tech going to be there? What's going on with them coming in on their equipment also? Have they wiped everything down? The top right, and this is a huge thing, is the blocking of return grills. This equipment set in here, all the contaminants are not being washed out of the room like they're supposed to be, and when these grills are blocked. And probably here is one of the biggest things, and a lot of it always gets pointed at the vendors that come in, and staff can be included in this. Are we wearing masks correctly? Are we gloved up when need be? Are our arms covered up? I know big thing in the implant world, there'll be vendors pointing on the back table, their arms will be uncovered, and they'll be over the top of the table moving around. And as Damon mentioned earlier, the humans inside these rooms, the staff and the vendors and stuff, help contaminate these rooms, and that's things where there's opportunities to transmit and trap pathogens in these rooms. In working with Dr. Wagner, we have learned that there are many opportunistic species of mold, bacteria, fungus in the ORs, and that they all are completely invisible to us till something happens. We've got to find a way that we can manage. We're finding ways to manage these opportunistic species in multimodal approach, whether it's nursing, facilities, infection control, environmental services, etc. And here, a perfect example of finding best ways to manage these bugs is a study looking at using HEPA filters for the intubation and extubation of patients that are either COVID positive or patients under investigation for COVID. The question was, is it better to run the HEPA during the entire procedure? So what we determined with this was, when we did run this during the entire procedure, the HEPA drew the contaminants actually across the sterile field, as you can see here in the map here, drew this contaminants across the sterile field, changing the desired flow of the room, and thus putting the patient at risk. At this point, I'm going to turn this over and let Dr. Jennifer Wagner introduce herself and jump in here and continue.
Thank you, Brent. Thank you, everyone, for taking the time to listen to our presentation this morning. I'm going to actually tell you about a study that we did about 1.5 years ago, maybe 2 years ago, that inadvertently led us to understanding this problem a little bit better. And so in this particular study, as we do in all research studies, we had a scripted procedure, but we had a real team, and this study was actually done in Australia. So we had a real team of surgical team that consisted of surgeons, scrub techs, nurses, circulating nurses, everybody that you see over on the picture on the left. So this full team was present with us through 9 different procedures in 3 different operating rooms in the same facility. And each one of the operations were designed to be completely repeatable, and the script that we followed was up on a monitor. And so we went into each one of these 3 rooms, and I'll describe what the different operating rooms look like in a minute. And we repeated this exact surgical procedure every single time. And so, of course, at this point, we didn't have a patient, we had a stake, and we used the stake for electrocautery, for suturing. Instruments are passed back and forth, light booms are moved, people are moving in and out, doors are opening and closing, very dynamic simulated procedure. And that procedure is also published, and many of you have probably heard us talk about that before. But this particular research study was intended to look at how an operating room performed to protect the sterile field. And we found, which you'll see, we found that information, but we also found something that surprised us at the time, which is what happens to the space around that sterile field when your operating room is performing to protect the patient. So these are the 3 different operating rooms. We had OR 5, 15, and 16. So OR 5 was an older OR, and it consisted of 4 four-way throw diffusers. So it was not a modern design. It was not compliant to ISHE 170. It did have HEPA filters at the diffusers. There was not the air distribution coverage over the sterile field. There were 2 return grills. It did not have your required positive pressure. And it did have, as you'll see, which is interesting, some air distribution coverage over the back table. Okay, so ORs 15 and 16 were new ORs, brand new. They had been used or in use for surgery for about 3 months before we went in to do our procedures. And both of these were designed, the rooms were designed exactly the same. They were mirror images of one another, right next to each other. And the only difference between 15 and 16 is that OR 15 had what we would consider a single large diffuser. So where all of the gaps to air delivery were minimized. So there were 9 diffusers in the ceiling, all right next to each other, with actually a proprietary design that prevented any disruption to the downward flow, directed downward flow of clean HEPA filtered air. So in OR 16, it was what we would call a multi-diffuser array. And so there were 6 diffusers in the ceiling, all providing air over the sterile field. Excuse me, but there were gaps to that air delivery. So there was hard lid ceiling areas where booms were mounted, and there was not that unidirectional downward flow of clean filtered air, which, as we predicted, would allow for some turbulence in the space. Additionally, this, which is a very realistic possibility in any given OR, is that the longitudinal axis of the multi-diffuser array was perpendicular to the orientation of the surgical table. So again, you can imagine now you have a bit of your sterile field, or what was supposed to be your sterile field, is not actually covered by clean filtered air. So this is, something that we might see because tables can be turned in order to accommodate different types of surgeries. And so that was a realistic differentiator. So in doing our experiments, we always rely on the industry standards that are out there. So not standards for operating rooms, but standards for clean rooms. And so our experiments are always designed around the ISO 14644 standard, the USP standards. And so one of the things that we do in order to look at the room as a whole, but not just one big box, we grid out the room and into different sectors. And so in this case, we had 9 different sectors within the room. And in each one of these sectors, we take particle counts, as well as other environmental quality indicators. And the particle counts and the other indicators are generally done at the height of the surgical table, which of course is, also within the breathing zone. But when you're worried about the patient, that's what matters the most, is what's going on at the height of the surgical table. So if we're looking at the results of this, and we looked at a number of different things. We looked at particle counts, we looked at microbials, we looked at humidity, temperature, air velocity, all of these different environmental quality indicators, or EQIs. When we look at the microbes, which of course is the one thing that matters if you're looking at an infection, whether it's a surgical site infection, a healthcare acquired infection, a virus, a bacteria, a fungi that is opportunistic and can cause a problem, that's really all we care about, right? The humidity, the temperature, air velocities, inert particles, all these other things are really profoundly predictive of your risk for an increase in microbial contamination. And that's really what we look at. But when we're doing our experiments, and these 100 experiments that Damon was referring to earlier, and over 500,000 data points, we also do look at the microbials. And this is how we know that these other EQIs become predictive. So when we're looking at these microbials in this particular experiment, what we found is that in the sterile field, so if you look at the graph on the right, in the sterile field, the single large diffuser performed statistically significantly better than either the multi-diffuser array or the 4-way throw diffuser at removing the microbes from the sterile field. If you look at the graph on the left, you'll see that the opposite is true, right? So the single large diffuser did not perform any better than the multi-diffuser array or than the 4-way throw diffuser. So now this really goes to exactly what we're saying, is this modern OR with a single large diffuser that has that unidirectional downward flow of air over the sterile field did a magnificent job of removing the microbes from the sterile field, but does nothing to address what's going on in the periphery of the room. And so now here again, if we look at the particles at the back table, so outside the sterile field, what we find is exactly what we now do understand, and what we've come to understand is that OR 16, so that multi-diffuser array where you had 6 diffusers around the sterile field with blockages to the airflow that was pushing things out, we find that the particles were actually less in certain size particles were actually less at the back table than the single large diffuser. And so that actually makes a lot of sense at this point, right? Because where you're performing better at the sterile field, all of those contaminants within the sterile field have to go somewhere, right? And so where are they going to go? They're going to go to the periphery of the room in order to get out through those return grills. And so here what we see is if we're looking at operating room 5, so the 4-way throw diffusers, you can see the sterile field, you can see the light boom, surgical table, back tables, where the locations of the particle counters were. All the little green dots are surgical team members. The dotted lines indicate movement, and so they would be moving around. Some of them are stationary, right? People standing around the surgical table generally stand still. Sometimes, depending on the procedure, they will switch sides of the table and things like that. But they're more stationary than the circulators or people going in and out of the doors and things like that. So what you're going to see here when the animation starts, here's the four-way throw diffusers that are located around that sterile field. And so they're delivering air into the room, but not in any controlled manner, right? It's not a unidirectional downward flow of clean filtered air. It's just clean filtered air kind of coming into the room. And that creates a risk picture that looks like this, where you see that you've got a little bit of filtered air in that sterile field, but as it diffuses out towards the perimeter, it's pretty uniform in terms of what that airflow looks like. So in operating room 15, which had the single large diffuser, again, you've got your people moving around, stationary people, back table, sterile field, light booms. In this, I just want to point out the light boom is off to the side. So again, you're not blocking that clean filtered air from that single large diffuser. And then you see the 9 diffusers over the sterile field. And when you overlay the risk map, as you can see, it starts out much cleaner in the sterile field where you have that very clean sterile field. But as you move to the perimeter of the room, if you remember in operating room 5, that 4-way throw diffuser was more uniformly yellow, so not quite as bad. But in this particular room, when you get to those corners and those edges of the room, you're approaching red. So you're approaching an area where all of those contaminants are being pushed to the perimeter so that they can get out of the return grill. So in operating room 16, the multi-diffuser array, again, you've got the same setup. Like I said, it was a mirror image of operating room 15, built at the same time, exactly identical room in square footage, layout, all of that, with the exception of the type of array that was put into the ceiling. And so here you're seeing those 6 diffusers in an array, which was perpendicular to the surgical table. And when you overlay the risk picture here, this is what you see. And again, you see a little bit of cleaner air within the sterile field, but then you see as it moves out, it's a little bit more uniformly yellow. So not as bad as the perimeter of the room in the modern operating room of OR 15. And I think that you will see when we look at all of these together side by side, you can understand exactly what's happening here. So when we are creating these operating rooms in this modern design, which is great for the patient, right? So the middle picture here, operating room 15, single large diffuser, protects that sterile field really well. But if you are a surgical team member in this operating room and you're thinking, I want to protect myself, I'm just going to move as far away from the patient as I can, you have potentially put yourself in harm's way of all of those particles and microbes and contaminants. I mean, it could even be something like surgical smoke, right? All of those particles are being cleared from the sterile field to the perimeter of the room. So this is what came to light and became very clear to us, which is the basis for the numerical portion of the paper that we published with Dr. Dexter of the American Society of Anesthesiology. So as I said, this study was done, a year and a half ago, maybe 2 years ago, published and everything. And all of a sudden, as we got into the coronavirus and questions started coming in, phones started ringing, where do we go? How do we stay out of the path of the virus? You know, how do these things work? And all of a sudden, this research now not only was important for protecting the patient, but it became important to protect the staff from the potential contaminants that the patient could produce. So in conclusion, OR5, which was our 4-way throw diffuser, was not as clean at the back instrument table as OR15 or 16, but it was also not as dirty at the perimeter as ORs 15 and 16. So the single large diffuser was the cleanest at the sterile field, but dirtiest at the perimeter. We saw that, right, in those risk pictures. And the multi-diffuser array was cleaner at the back instrument table compared to OR5 or the 4-way throw diffuser, but not as clean as 15 and not as dirty at the perimeter as OR15, but it was dirtier than OR5. So the limitations really are notes. There were differences between the cleanliness of the environment at the sterile field and the back instrument table, and then ranking OR 15, 16, and 5 from cleanest to dirtiest. At the sterile field, 15 is still cleaner than 16 or 5. And the level of cleanliness was dependent on the air filtering and the air distribution. So just to drive that point home, just air filtration, just pressurization, just air changes, not a single one of those alone is a silver bullet. It's all of it together, and it's really understanding how and where your air is moving and using that, optimizing that air, movement, direction, air changes, all of that together to control the contamination in any given space. So Damon, I think you were going to wrap this up.
Yes, I'll wrap it up with a reconnection with our learning objectives. So as far as standing at the wall during an aerosol generating procedure, you know, we determined that you are, as a staff member, at greater risk and you would need to be isolated. And the reason I put the hierarchy of controls, which is a general, you know, format and framework for infection prevention, is that elimination and substitution, right, the two primary drivers, affect the built environment. And I know as an engineer and many of my engineering colleagues, we love to have permanent solutions, right, that work to eliminate or prevent problems. However, we also have to be careful not to create unintended consequences, right? So if we're trying to protect our staff, we should not be putting our patients at greater risk as a result. Because patients, right, they are the most vulnerable during these procedures. What can a facility do to better understand moving air? They can change the way the staff works, right? So if the staff is able to be in a better risk position, right, or there's a better ventilated portion of the room for which they are to stand, if they're just idle, then that can be used for optimization. And because a modern OR is concentrated air delivery over the sterile field, we would also prefer that to be the back table and back instrument table as well. But if you are going to be at the periphery of the room in the direct pathway of returns or exhaust, we do know that PPE is required. And of course, that's way beyond COVID, right? That would be any infectious organism that could be aerosolized. The beacon algorithm that we use is vital. Facilities have now begun to really depend on the information that it provides. This is just the surgeon, orthopedic surgeon, that said that, you know, if his administration wouldn't pay for it, he would, because he cares about the safety of his patients, right, and as well as the reputation and costs when patient harm occurs. And we're now going to open it up for questions.
If you have questions, go ahead and type them into the questions panel on your desktop or laptop, wherever you are viewing the presentation. And I do have a few that are in. So Damon, here's the first question, and I don't know if you'll answer this or if anyone else wants to jump in, but the first question is, if the virus is going to the perimeter of the room, do you recommend negative pressure?
Sure. So the one thing that we have to understand if we're considering negative pressure is what that really means long term. So if your room is negative pressure, that means that it is pulling or sucking in contaminants from your envelope, your ceilings, your walls, your floors, the hallway continuously, right? So you are continuously building up embedded contamination in that room. And the University of Pittsburgh Medical Center actually did a study, I think it was 2 years ago, where they converted airborne infectious rooms to protective environment for neutropenic patients, and they killed several patients as a result. And that was a hard lesson to learn, but it's something that we should always consider in our risk assessment. The other thing to consider is the difference between virions, or RNA material that is just floating in the air, right? We found it in ducts, we found it in hallways, but is it really an infectious aerosol that is a dose that is going to be deposited in a caregiver or potential patient's lungs, even with the universal masking mandate? So that is definitely a consideration. And finally, we've generated a literature review between the top 20 organizations that are advising around procedures, trauma rooms, or operating rooms. And they all agree that only for airborne infectious isolation procedures, bronchs, should they keep the room negative. Otherwise, they don't recommend it. They recommend remaining positive along with airborne precaution.
Okay, good. That's helpful. Here's a second question. Are HEPA filters effective in capturing the virus?
Sure, I can take that one. Yes, they are. That's the short answer. And there is a landmark study that was conducted by NASA. I don't remember the year, but where they looked at the efficacy of a HEPA filter on small, super small, nano-sized particles. And what they find, and the reason that you'll see that a HEPA filter is rated based on 0.3 microns, because a 0.3 micron size particle is the hardest to capture. It's harder to capture than something larger. It's harder to capture than something smaller. And the idea is that once you get to be as small as a virus, you're subject to Brownian motion. And the fact that they move back and forth and wiggle around in the airstream does make it so that the HEPA filter is effective at capturing the virus.
Okay, good. Here is a third question. This question is, how often should doors be allowed to be open during the case?
This is Brent, and I'll take this one. As a nurse, looking at as little as possible, but also with a caveat, it depends which doors we're opening. If we're opening if somebody has to come into the room, coming in from the sterile core is absolutely the best way to come in. Going in and out of the patient door, in and out of that door during the procedure, especially when skin is open, is not a good, is not a best practices. Seen it done many different ways, especially in the orthopedic world during total joints. Many of the surgeons will not allow doors to be opened when they have the skin open. So that is when skin is open, doors should remain closed, especially in high risk cases, but as little as possible is the best answer.
Okay, good. We have a few more questions here. The This one is, should the laminar diffuser array be expanded to cover more of the room with the goal of making the room more sterile? So again, should the
I'll
laminar...
take this one,
Okay.
Dave, and I can say that we have proven this to be effective in reducing contamination. We actually worked with one of our sponsors for this presentation, BSA Life Structures, to improve upon the air delivery with economics in mind. We didn't add a significant amount of coverage for unidirectional airflow, but we did provide protection for the back instrument tables when they were moved into position during the case.
Okay, good. There's a kind of a follow-up question on the HEPA filters, and that is, what precautions need to be taken when changing HEPA filters?
Sure. So from a maintenance perspective, you know, HEPA filters have a gel seal, so they really should be bagged in for cleanliness and confirmed to be sealed properly within the housing. And then, of course, when you're removing those, you should treat those as a hazardous, contaminated device or condition, and so there should be a bagging out process for removal.
Good, that's helpful. So here might be the last question, but we'll see what pops up. This is probably a good summary question. Based on what you have seen, do you believe improvements can or should be made to current air delivery codes and standards? So again, based on what you've seen, do you believe improvements can or should be made to current air delivery codes and standards?
Yeah, it's a good question. The one thing that codes are, especially in the United States, are parametric, right? They are just protocols, right, or parameters to design to. And we also know that codes are nominal, meaning that they are in name or number only. And, you know, for those of you who are members of ISHE, you're aware that ISHE 170, and I commend them for doing this, actually had two independent universities, Nebraska and Clemson, study their over 800 parameters. And I think they found only 165 were evidence-based. So we do need to modify our codes based on evidence, science, and research, and also adapt them to be more performance, right, quality related instead of just parametric and nominal.
Okay, good. Thank you. So at this point, Vic, do you want to go ahead and wrap us up?
Yes, that was a great presentation and great information. Thank you, Damon, Brent, and Jennifer. I want to thank everyone for joining us for this webinar. We invite you to join us again next month on December 2nd webinar, in which we'll hear from Hospital Association leaders from Indiana, Ohio, and Illinois. You can learn more about that webinar on the ISHE website at www.isheweb.org. I want to personally thank all of you for doing what you do best. Have a great day and be safe.